dozen different sources from the period say something very strange. They say basically that the sun disappeared.
Witness a world where nature reigned supreme and catastrophe rewrote the story of civilization.
Huge volcanic bombs are coming out of the sky, these great rocks, about 3 feet across, crashing through the material.
In the ancient world, disaster was always lurking. Earthquakes and volcanoes flattened and buried mighty cities in an instant. Drought and plague wiped out civilizations without mercy.
So if you've got an empire, that too becomes immensely vulnerable and prone to collapse.
Life in the ancient world often hung by a thread. Over the next 4 episodes, we'll discover that survival was never guaranteed.
It's like playing Russian roulette with 5 bullets in the 6 holes.
It's time to step into the chaos and witness the catastrophe, to uncover how disaster reshaped civilizations and the world itself. This is Great Disasters. It was the biggest mass extinction event in Earth's history. 250 million years ago, a rich and diverse prehistoric world on land and sea was wiped out. 97% of life on the planet was extinguished. It's called the Great Dying for a reason. This was the Permian Extinction. In this episode, we're going to explore what we know about this most catastrophic of all extinctions. We'll highlight the rich and diverse world that existed beforehand, the many different bizarre species that lived on land and in the sea. We'll delve into the extinction itself, what we think happened, and, perhaps most fascinatingly of all, find out why and how 3% of life was able to survive. This extinction event ultimately paved the way for the rise of the dinosaurs. This is the story of the Permian Extinction, episode 4 of our Great Disasters miniseries with Professor Michael Benton. Mike, it is such a pleasure to have you on the podcast today.
Thank you very much indeed, Tristan.
There are extinction events, and then there is the Permian extinction. This is the biggest that ever hit the Earth.
That's right. We talk a lot about extinction today. We're aware of species going extinct, and I think most people worry about that. When we go back in time, we discover larger extinction events like the end of the Ice Age and the death of the mammoths and other large mammals. Many people are familiar with the end of the dinosaurs 66 million years ago. That was a mass extinction, so-called, because lots of species died out. But it's estimated only 50% of species, maybe 50, 60 went. The biggest of all time was indeed at the end of the Permian 250 million years ago. And it's estimated that more than 90%, even 95% of species went out.
So 250 million years ago. So Mike, this is a time long before the rise of dinosaurs.
Yes, and so many people think the Earth started with dinosaurs, but of course dinosaurs were quite late arrivals, and there had been millions and millions, indeed billions of years of history before that. And indeed, dinosaurs, when they appeared, were side by side with some of the first mammals, our ancestors. So this is really, to a geologist like me, quite modern times. And the end Permian event was considerably before the dinosaurs.
I love it when we get an expert on the show who calls the age of the dinosaurs like more recent modern history.
Yeah.
and it's always the case with geologists, isn't it? Especially when we're going this far back. I mean, I guess the clue is in the name, a geologist, but what types of evidence do we have to learn about this mass extinction event from some 250 million years ago?
What geologists do is look at the rocks. I think people are familiar with the sequence of rocks, the oldest at the bottom, the youngest at the top. And as we go around the world, rocks of different ages are preserved. We map them. You can see them on maps. The ages are established in various ways. And for this particular time, at the end of the Permian and the beginning of the Triassic, and I should say these names, Permian and Triassic, are what we call the names of geological periods. They were established a long time ago in the 1830s and 1840s, in the very early days of the science, when geologists realized that you could find rocks of the same age in different parts of the world. And more or less at that time, they recognized the same age by the same fossils, indicating the same kinds of plants and animals living at the same time. And it just so happens for the Permian-Triassic boundary, there are sections in North America, in Europe, close to where a lot of geologists live, but the best ones are in South Africa, Russia, China, Pakistan. So for Europeans and North Americans, these are more exotic parts of the world. But it's been huge fun for me traveling to see these locations and working with scientists in those countries.
And is it within those rocks that you get the information like the fossil remains, the information about climate and so on?
Yes, let me just describe what we saw as we approached the Permian-Triassic boundary. So that's the exact level at which the crisis happened recorded within the rocks. In Russia, we were doing field work on the border between Europe and Asia. This is at the south end of the Ural Mountains, on the sides of the Ural River, which is a huge river. And we were walking or driving initially, then walking across, and we pointed out to our Russian colleagues, well, what are these craggy hills all around the edges? And they said, oh, that's Triassic. And how do you know from such a distance? Oh, well, there's just an enormous change in the topography, the way the rocks are being deposited. And as we walked up the slope and through the thick grass of the steppe, you could see that it was soft sediment, it was clay, it red colored, but it was quite fertile and everything was growing happily. And then these tall vertical crags of very coarse rock, which we would call a conglomerate, made up of boulders that had obviously been tumbled and dumped at some former time. And so they noted the boundary, and it corresponded to a huge change in topography, indicating something about the climate. And how would you explain this switch from what we were in the Permian seeing, the uppermost Permian, which were deposits of ancient meandering streams? If you dial back to your geography lessons, meandering streams mean generally low energy, fairly gradual slopes, and quite lazy rivers just tootling along and nothing much happening, animals happily drinking and feeding and occasionally dying and getting preserved. At the boundary, suddenly this rush of sediment, meters and meters being dumped very rapidly, containing boulders up to a meter across. And the Russian geologists had traced these boulders back up into the Ural Mountains, where they could determine pretty much where they came from. These were much more ancient rocks that had been then eroded from the high mountains in the Urals, which existed at that time and were probably much higher and have been eroded since, and then being tumbled down the mountainside and forming great alluvial fans. Again, dial back to your geography lessons. An alluvial fan is a great semicircle of sediment that comes rushing off a mountainside. And as the gradient changes, the river flow slows, and it dumps all of this jumble of rocks and stuff and logs and all sorts coming down the mountainside. So this is what we were seeing. And they had mapped these alluvial fans that had formed 250 million years ago. And some of them were 100 kilometers wide.
Wow.
So, and that indicates the scale as they flow out. And how do you explain it? They explained it by a new phase of mountain uplift, that somehow the Urals were being uplifted rapidly and hence steepening, and hence you get more erosion. The other idea they'd had, but they'd rejected, was increased rainfall. If you suddenly increase the rainfall, you can then release and wash down huge amounts of material. No evidence for that in the rocks. The geochemistry and clay minerals in the rocks showed actually it was getting drier. This is a time of considerable high temperature. We, though, debated with them because we were aware that people had found the same phenomenon in South Africa, China, other parts of the world. You seem to get this big sediment shift on land. What's happening? It can't really just be what geologists would call local tectonics. Tectonics is earth movements, and this would be a bit of plate tectonic movement and uplift of the Ural Mountains. That wouldn't explain things happening tens of thousands of kilometers away. So the only other explanation we thought of, which I now think is widely accepted, is deforestation. If you remove the plants, particularly the trees, from a landscape, particularly from a hillside, as we see today, in Brazil, in Pakistan. You cut down the trees, then the soil is released and you're left with a rocky slope and great amounts of sediment, which are kind of stabilized. Forests stabilize the landscape. And so this is what we think was happening. And then dialing back, why would the forests go? There were no human beings then cutting them down. Acid rain. Acid rain comes from excess carbon dioxide in the atmosphere. And so after a lot of debate and discussion with our Russian colleagues, they accepted that. And colleagues in China and South Africa and other parts of the world who were discussing this, what you could call a sediment pulse, they agreed, yes, okay, this is a really catastrophic landscape scale change, but happening worldwide. And this is a clue to the bigger picture of what was going on.
That's a tantalizing cliffhanger to leave us on at this moment in the chat, and we will revisit then what we think the bigger causes are as we go on. But first of all, we need to paint a picture of this Permian world before this mass extinction event. And first of all, Mike, can you explain, I know it's a big question, but give us an overview of how the story of the Earth, how we get to the Permian period, because I know there are several other periods that precede it.
Yes. So 250 million years ago is the point in time we're looking at, but the Earth is pretty widely accepted to be something like 4, 5, 6, 7 billion. That means 1,000 million years old. It's an easy number to remember, 4, 5, 6, 7 billion. And when the Earth formed, it's difficult to see the record because however it formed, surface rocks were molten, not surviving. It was very active and dangerous kind of volcanic landscape. And probably at high temperature, of course, nothing we would recognize as living could exist. And then something like 3.5 billion years ago, the first traces of life are found. They are very simple, microscopic, virus-like organisms, similar to the very simplest organisms today. And over billions of years of what is called the Precambrian, this is the bulk of time up to something like 550 million years ago, life diversified. And by the end of the Precambrian, we do get visible, macroscopic, we call them, visible organisms, plants and animals like seaweed-type plants in the oceans and simple organisms on the sea floor. And then comes the Cambrian explosion. So the Cambrian and the following geological periods, which I'm not going to catalogue in detail, they are named after rocks in Wales. So I'll derive the Cambrian from the Cambraes, an ancient tribe. And with great imagination, the huge amount of time before the Cambrian is called Precambrian. Why not? And then we go through time with steps. The Cambrian explosion is when we really get a burst of animal life in the oceans. And the precursors of lobsters and clams and oysters and even fishes and all the different typical marine animals we think of pop on the scene at that time in a phase of quite rapid evolution. And during the time between 550 and 250, the end of the Permian, we get the formation of the first reefs with sponges and corals and different creatures. This is a whole new kind of system of high biodiversity that we're quite familiar with today. There were different species, different major groups of corals and sponges at that time. The concept of a reef as a structure and so on continued. And then something like 400 million years ago, life began to creep onto land. At first it was plants, and yet they kept their roots in the water, of course, mainly around the edges of fresh waters, perhaps, rather than the sea. And with plants, initially some insect ancestors and little worms and other terrestrial creatures gradually crept onto land, and you find the first evidence of soil. Soil is a product of life on land. So even though there aren't very clear fossils of some of these early worms and other creatures that were churning the earth, the fact that you find the earth, the soil, tells you there's some sort of life. And so it goes on, and we have the great coal forests. People have seen pictures, I'm sure, of the Carboniferous in Europe and North America, all of the coal.
With those giant centipedes and dragonflies.
Exactly,
and the like.
giant everything, giant trees, giant seed ferns, weird sort of trees, not like modern trees. And yet they were big. And as you say, living amongst them, giant centipedes and giant dragonflies the size of seagulls and all sorts of amazing things. And at the same time, vertebrates, us, were creeping onto land. You get early amphibians and early reptiles in the Carboniferous. And it's the famous geological period. It was the first one to be named because it has these economic stocks of coal. And Carboniferous means coal-bearing in the French. And the Carboniferous is followed by the Permian. And the Permian saw the great diversification of reptiles, and climates generally were quite hot. Most of Europe and North America, and indeed a lot of Asia, were located around the equator. And during most of the Permian, there were no ice caps. So the range of temperature from equator to pole was much less than it is today. And so temperate climates were more warm than they are today. And so across the Permian landscape, and we can see the evidence in South Africa, Russia, North China, other places, in these rocks in Russia that we were working on, there's great evidence of what life was like at the very end of the Permian. And at the top of the tree were some huge herbivores that weighed a ton, called pariasaurs, the size and shape of a hippopotamus or a big hippopotamus. But they had armored skin. And so they had armor plates all over. They had very short legs, quite small heads, and knobbly heads. So I'm sure their mothers loved them, but to us, they looked rather hideous. But they were stomping around. These are called pariasaurs. They were stomping around, feeding on plants. And when we were working in Russia, we even found evidence of their wallow pits, so that in the hot heat of the day, they would wallow in the mud and probably flick mud over themselves like modern water buffalo and hippos do today. And they were preyed on by saber-toothed reptiles called gorgonopsians.
Hang on. What? Wow. You think saber-tooth, you think Ice Age?
Yes, you do. And so this is to really emphasize how advanced the ecosystems were at the end of the Permian. And indeed, yes, these saber-toothed gorgonopsians, which indeed were reptiles of a sort, distant ancestors of mammals, and they had long saber-like teeth, presumably to penetrate the thick skin of the pariasaurs. And like the saber-toothed cats that people have seen, it's not just having that long tooth. You've also got to have a lower jaw that really swings down, because if you're going to drive that tooth in, you've got to expose the entire tooth. And it means their lower jaw can swing back to a ridiculous extent. I don't know how far we can open our mouths, but they could open them 90 to 100 degrees. So really wide gape. Drive in the tooth. And I think like saber-tooths, they don't hang on and wrestle. They just pull out and watch. And the poor victim will eventually trail about and die because of loss of blood. And then beneath these in the food pyramid, if you like, there are smaller herbivores, there are smaller carnivores, all the way down to reptiles that would be feeding on insects. And there were all kinds of cockroaches and other beetle-like insects. And there were also spiders and centipedes, so plenty of prey. And as well, fish-eating amphibians in the rivers.
Do you also get almost proto-mammals at this time?
Yes. So a number of these carnivores, particularly the ones feeding on insects, they are proto-mammals. So this is the beginning of our lineage was there. And, we can always speculate what would have happened if the crisis had not occurred. Would the pariasaurs and the gorgonopsians have carried on, or because they were killed off, or would it be the little ones which eventually prevailed and became the mammals? Or indeed, there were other lizardy kind of creatures that were the ancestors of dinosaurs. They were creeping about in the undergrowth as well, but you wouldn't have picked them out as future rulers of the earth.
Ever wondered what it was like to plot the assassination of Julius Caesar?
To stage the Boston Tea Party?
Or to orchestrate Blackbeard's final stand on the high seas? I'm Matt Lewis,
I'm Holly Nielsen, and we're the hosts of Echoes of History, the podcast that goes behind the scenes of the iconic game series Assassin's Creed. We're on a mission to uncover just how the game creators recreate all of the most nail-biting, pivotal moments in history, from the bloody Ides of March
To the rise and fall of a pirate republic.
So grab your hidden assassin's blade and blueprint
And join us every week on Echoes of History, a Ubisoft podcast brought to you by History Hits.
And also, before we go to the marine world at this time, the land that these animals, these various types of animals are living on, should we be imagining continents, like some species would not have interacted with others, or were they all together just on one continent?
That's a very important point. And they were all together on one continent that is called Pangaea, the whole Earth in Greek. And Pangaea stretched more or less from the North Pole to the South Pole. We have to imagine a world where there is no Atlantic Ocean, so the Americas close up against Europe and Africa, and all of the southern continents, including Antarctica and India and Australia, they were all fused together in the South Pole, and Asia and much of China. There were various islands offshore that were part of South China, and the evidence of the fossils shows that you find very similar species were crossing the equator, were wandering up and down from north to south. And there weren't the kind of strict climate belts that we get today, which separate species. But also, you're right, very importantly today, having many separate continents means that keeps very different faunas and floras in each part of the world.
And talk to us about the marine world at this time. I mean, if the land terrestrial world is extraordinary, I feel the marine world, given that it's had life living in it for much longer, will be even more extraordinary.
It was certainly rich and diverse. Whether we can say extraordinary, I'm not so sure. That's all a human perception, I suppose. But the oceans were full, and there's very good evidence from North America. There were enormous reefs of corals and sponges and various other creatures fixed essentially to the seabed and filter feeding across much of Texas and the southern United States. And they have yielded millions upon millions of fossils and an enormous knowledge of the diversity of these reefs. And then swimming above the reefs were some early sharks and bony fishes. And there were also swimming cephalopods, sort of squid-like creatures, octopus-like creatures, but many of them contained within a shell. Some people may be familiar with ammonites. Ammonites are those coiled ones that start in the center, coil out, of many different shapes, and they existed before the extinction event. They became very important afterwards. We often associate them with later spans of time, like the Jurassic, but they were there. And some of those swimming cephalopods were pretty big. Some were several meters in length, and so they were pretty scary predators. And there's a huge amount of evidence also known from more recent work in South China, which has shown a great deal of detail of these reefs and different depths of water and the richness of life that existed.
Should we mention the prehistoric Permian T word, as it were, the word trilobites?
We should. I didn't bring up trilobites because they were dwindling. They were quite rare by the end of the Permian. But indeed, you're right. Trilobites are a very familiar fossil from Cambrian onwards, really. They did go extinct at the end of the Permian. They're called trilobites, meaning three-lobed, because they are divided into three lobes. There's a middle portion with a kind of head and a tail and many segments, and then a lateral portion to which the legs are attached. So they look like overgrown woodlice, and from the size of a woodlouse, with some of them up to maybe 0.5 meter in length. And they were very active feeders in the floor of the ocean. But for whatever reason, nobody knows quite why, they had dwindled quite a lot by the end of the Permian, so they weren't that common. And so there were a lot of groups then of trilobites. There were brachiopods, that's a group that still exists, but these were shelled creatures that were hugely important before the extinction event. and various groups like crinoids. These are sea lilies. They were part of the reefs. And generally, they consisted of a stalk made out of separate rings of calcium carbonate skeleton. And on top of the stalk was a kind of cup-like head with tentacles, and they would be filter feeding. So to the specialists, there's a great diversity of organisms, but a lot of them are not so familiar to the wider public.
So you've painted this wonderful picture of the Permian world, Mike. And so giving this idea, as you say there, almost to repeat, lots of different animal and flora, faunal groups, and lots of species within those different groups as well. So it's almost like going down a pyramid. So you have the group at the top, then lots of species below within that group, kind of branching off from it. And that really epitomizes the great diversity and variety of life at that time.
That's right. And I think that ecological way of thinking is a good one. We're all familiar, I think, with the idea of a food web, where you write down all the species that live together, and you write down lion feeds on antelope, and you put an arrow from the antelope to the lion because that's the direction of flow of energy. Then the antelope is feeding on grass, so you have arrow to arrow to arrow. And of course, as you build this up, it becomes quite complex. But you can do that equally with these fossil assemblages. And that's been a very fruitful way to work. You pick locations in the world where there's fantastically good documentation. It's often said that, of course, the fossil record is very poor. Well, in some regards, of course, it is. We lose a lot of information, but there are locations where you can do this. And then you can test the stability or resilience of these food webs. And by the end of the Permian, they were complex and they were resilient. They were very stable, which indicates long periods of evolution, good adaptation. They were well fitted for their jobs.
And so we get to the end of the Permian, Mike. What do you think happened?
What do I think happened? I think I have no original thoughts on this other than the generally held view that people had noted something quite extraordinary had happened at that point. And indeed, from the very early days of geology, the distinction between the first span of time that we've been talking about in general, from the Cambrian to the Permian, was called the Paleozoic. This is in the days of Darwin. This was by 1840. The name had been developed. Paleozoic meaning ancient life, that's the world of trilobites and crinoids and early corals and such like, followed by the Mesozoic, which begins with the Triassic. They noted this extraordinary change, disappearance of so much and appearance of so much. And yet when I started in the subject, people were still debating, well, maybe this happened over 100 million years, 50 million years, nothing much to look at. So it's extraordinary to realize how recently this has all come together as a real model or picture of what's happening. We now know, by looking at evidence from China, where there's very good quality rock dating and very good evidence, that there were two levels of crisis, two particular levels of crisis, separated by as little as 60,000 years. And at the first level, something like 80% of species disappeared. And by level, I mean literally you're looking at the rocks, and within a centimeter, you can see this crisis, this first step of the crisis, near the end of the Permian. And yet the complexity of the ecosystem was sort of maintained, oddly. And then a second hit happened 60,000 years later, near the beginning of the Triassic, and another 80% of species disappeared. But at that point, the ecosystem collapsed. And collectively, 80 plus 80, with originations happening in between, comes up to something like 96% of extinction. So the recent work has really allowed us to focus in on the time scale so much better than maybe 20 or 30 years ago when I started to be interested in this. And the reason that the dating is so good is that there is radiometric dating, that is exact age dating from zircons, which are particular minerals that were formed at the time and are preserved within the sediments. They can be dated with potassium, argon, lead, uranium dating, down to fractions of million years, down to 10,000 year kind of scale, which is just astonishing, that level of precision. And luckily, because of certain events, we've not got to the smoking gun, but we're coming towards it. There are ash beds. They can be sampled and the dating can be done. And so we're able to measure the scale of that crisis in a quite precise way.
And it's important to highlight, I mean, if you mention 10,000 years today, that's between where we are now and the end of the Ice Age. So we think that's a massive amount of time, so much development in the story of humans and so on. But when we're going this far back, 10,000, 60,000 years, it's pretty close when exploring these catastrophic events.
When I started, we were taught that errors on dates were plus or minus 5%. And so when you get back to that time, this is plus or minus 5, 10 million years, even 20 million years of error. And so when you've got that level of error, you're just floating in the dark. I mean, you've got no way of pinning it. But now you're right, 10,000, 50,000 years to us is a huge amount of time. But to geologists, we think, blimey, this is pretty good. And I think because it's cross-checked, I think that's the reason we're reasonably confident that different labs use different isotopic methods and they cross-check. And they're somewhat competitive. Scientists, of course, always want to be right and would like to show that their competitors are wrong. So this is what we more normally call the self-correcting property of science. If somebody makes a mistake, we're not discreet about it. We're not tactful. We point it out pretty quickly. And so I've seen this to and fro of debate has moved very rapidly. And I think now we can be fairly confident.
So we have this evidence. What do we then think is the cause? What do we think is the smoking gun? Let's continue the story, Mike.
Yes. So we were creeping around the edges there in Russia. We discovered this very important phenomenon of the mass rock flow, the huge alluvial fans. But that was only part of it, because over the same time, back in the 1980s, 1990s, people were looking at marine sediments, and they noticed just at the boundary, they went anoxic. They went black. They had a huge amount of carbon, and that made them black. And that's unusual, because normally shallow marine sediments will not be black, because organisms eat the food. They eat the carbon. The carbon is coming from life. Is coming from plankton and other living things. And of course, if there is a supply of food, organic matter falling on the seabed, there's always going to be something feeding on it, drilling around, moving around on the surface, slurping it up, going into the sediment, burrowing, slurping it up. So the fact is that, and the chemical evidence showed there was a lack of oxygen, which is what we call anoxic, and it can be associated with iron sulfide, pyrites, the sort of sulfurous smell you get if you walk through a puddle full of leaves in autumn. It's rotting. There's nothing there feeding on them. The leaves go black. You can get the sulfurous smell. That's anoxia. So putting these two together, how do you get massive rock flow coupled with deforestation, possibly acid rain, and a stagnation on the ocean floor? Because stagnation on the ocean floor means that there's a cessation of the normal kind of circulation of the ocean. So in the ocean today and in the Permian, there would be circulation of water, cold at the bottom, warm at the top. And the circulation brings that cold bottom water up to the surface where it gets warmed. And indeed, it's that warming, that simple atmospheric warming, that generates this radiation. And the warm water will dive somewhere else in colder conditions. Today, it's in Antarctica. And that drags oxygen down to the seabed as the warmed water goes down. And then it gets colder because it's further from the sun. But that oxygen is needed on the seabed. Otherwise, life cannot exist. So to stop the normal circulation takes a big crisis of some kind. And so putting that all together, people noted that there were huge volcanic eruptions happening in Siberia at about the time. But at that point, they were not very well dated. They were just known to be maybe Permian, maybe Triassic in age. But these volcanic eruptions were represented by enormous fields of basalt lava, black lava that forms layers which represent the flows of lava. This is what we see in Iceland today. And so the kind of eruption is not the pointy Plinian volcano like Etna and Vesuvius. It's the long fissure volcano like we see today in Iceland. And although it's sort of more peaceful, people live on Iceland, they're not being overwhelmed by lava all the time. Sometimes they are. It's bubbling up the lava kind of all the time. And that's what was happening. And this must have been occurring on a much bigger scale than in Iceland today, because it covers millions of square kilometers of Siberia. And the volumes of lava are almost beyond calculation. They're millions of cubic kilometers, just enormous amounts. And the layering shows us that it was happening over a long span of time. And it's possible to date the different layers. So people didn't want to go to Siberia because it's not a great place to go. Politically, it was difficult in Soviet days. And in winter, it's damned cold.
Yes.
In summer, the mosquitoes are extremely large, I can tell you. And it took a long time for people to get in there, but they did. And the dates now show that they span the Permian-Triassic boundary over 1 million years, roughly. They started up before the end. They carried on into the Triassic. And so the whole picture has now been put together by studying modern volcanoes. It's not the lava we care about, it's the gases. And there are two kinds of gases coming out of any volcano, and including these Siberian ones, which are sulfur dioxide and carbon dioxide primarily. And the SO2, the sulfur dioxide, comes out quickly and quite early on, maybe in the first day or two of the eruption. That has a cooling effect, but it has a major acid rain effect, because when you mix sulfur dioxide with water, you get sulfuric acid, battery acid. And so even dilute battery acid falling across the world kills the trees. So that's the first thing, acid rain. Then the second is the carbon dioxide and methane and other greenhouse gases. They cause warming. And they actually come out for much longer, and they have a much longer lasting effect. So there's nothing like a cancelling out of the cooling and the warming. The warming actually takes over and dominates. And the evidence from ocean sediments around the world is that temperatures rose by as much as 10 degrees centigrade. And we're worried about like a 1 degree centigrade rise at the moment. So think of how that's affected climates and hot summers and storms and hurricanes and all kinds of stuff. Just 1 degree, 10 degrees. So acid rain plus warming. So I'll just take that through. The CO2 then is pumping out. The acid rain is killing the trees. And after a year or two, the dead trees will fall and they'll eventually clear. And the landscape then shows this clearing and huge boulder movement, alluvial fans. And there is a lot of evidence of sediment and organic matter washing into the oceans. And that's being picked up. It's just a spike at this point in time of huge amounts of terrestrial stuff, plants and organic matter and soil and silica being washed into the oceans. But the warming also has a severe effect. It doesn't just kill things instantly, but we can see the effect of 1 degree today on tropical zones. The Sahara Desert is getting bigger by kilometers a year. People and wildlife have to move. And likewise, those temperatures are being felt in India, in parts of South America, in South China, and so on. And areas are becoming uninhabitable, not only for humans, but also for plants and animals, because we think, oh yeah, there's lots of stuff can live in the desert. You've got camels and cactuses. And you think, no, they're not happy. They don't like it. And biologically, nothing can really survive comfortably above about 32 degrees. So when you have normal summer temperatures of 32 to 35, increasing them to 40 or 45, it just drives everything away. So all of life over a wide tropical belt would have moved north and south. And because life in the tropics, in the oceans and on land is enormously diverse then as it is today, you are shifting 70 or 80% of global biodiversity is then living in uninhabitable zones. They crowd into the areas they can survive, but they're done for. And so it seems to be, if you have volcanic activity on a big enough scale, it can have this crisis effect. And it's called a hyperthermal, meaning high temperature. The hyperthermal crisis is a general term for this kind of phenomenon.
Ever wondered what it was like to plot the assassination of Julius Caesar?
to stage the Boston Tea Party,
or to orchestrate Blackbeard's final stand on the high seas. I'm Matt Lewis.
I'm Holly Nielsen, and we're the hosts of Echoes of History, the podcast that goes behind the scenes of the iconic game series Assassin's Creed. We're on a mission to uncover just how the game creators recreate all of the most nail-biting, pivotal moments in history, from the bloody Ides of March
To the rise and fall of a pirate republic.
So grab your hidden Assassin's Blade and blueprint
And join us every week on Echoes of History, a Ubisoft podcast brought to you by History Hit.
So, Mike, to get more of a sense of the scale of this volcano today, if someone mentioned supervolcano, I would think of Yellowstone or something like that. But was this eruption, that occurred, the first eruption that occurred in Siberia, is it much, much bigger than that? And to a scale that, even if it is just one eruption at the beginning, it pumps out so much, and it is, it's so massive, it covers the entire world, and the consequences is acid rain falling down continuously, causing desertification, in much of the landmass of Pangaea for not just hours, days, or months, but years and maybe even decades.
I think you're right. I think the term supervolcano is quite right. These are the kinds of massive eruptions that had occurred in prehistoric times. We get records of them from ancients, but I don't think any human has witnessed a volcanic eruption on this particular scale. And there have been others in the history of the Earth which also caused extinctions. And so we do think that this is a generalizable model, hyperthermal model. And when eruptions happen at any scale, all of these consequences occur. So people may remember Mount St. Helens, and it had some of these effects. But even though it was harsh for the people who lived nearby, that was a very small scale event. But there's lots of measurements that show that you can make a definite relationship between the scale of the eruption, how long it lasts, and how much lava comes out, is proportional to the amount of sulfur dioxide, and hence the amount of acid rain, is proportional to the amount of CO2, and hence the amount of warming. So humans have never witnessed a global scale super volcano like this.
And do we think that there was a follow-up eruption, or there was more than one eruption that just adds insult to injury and makes this event even worse?
There's been a lot of evidence for quite a long time that wherever the volcanoes were, there were pulses of global warming happening through the following 5 million years. So without a doubt, another 3 or 4 major pulses happened. So each of the events is probably, ecologically speaking, quite long-lived, hundreds of years, maybe even thousands. On a geological scale, quite short term. But life gets back to normal, and then 1 million years later, there's another hit. So there's good evidence through the early part of the Triassic for repeated hits. And one of the debates, or one of the sources of study at the moment, is to determine, is this because of continuing eruptions of the Siberian traps, or some other big volcanoes happening in Southeast Asia? There's evidence of other volcanic eruptions.
So you have the destruction of these tropical landscapes, you've got acid rain, you've got climate change. But how does this destruction also cause a great loss of oxygen?
Yes, so this doesn't necessarily explain extinction in the oceans. Of course, the surface waters get very hot, and swimming animals like fishes and sharks are not very comfortable. They try to go deeper, but then the amount of oxygen maybe diminishes. And the reason for that is that when you heat the surface waters of the ocean, the thermocline, which is that level within the water between warm water above and cool water below, people may be familiar with the term thermocline in lakes. In summer, the lake thermocline goes down. So here the ocean thermocline was driven far deeper than ever before, even down to the seabed, which might seem to be okay. But the effect of driving the thermocline down to the seabed in the shallow oceans is it perturbs or stops the normal kind of circulation. So it's a sort of swamping effect that at first is matched by a great burgeoning of life, like the sort of algal bloom that may happen in a highly perturbed lake that's overheated, full of fertilizer. And you think, oh, that's great, full of life. But it's not natural life. It's just swamping out everything else. And so I think it was the cessation of the normal circulation meant that the bottom of the ocean may have been warm, but after 6 months, it was deprived of oxygen because the regular flow had stopped. And therefore, reefs died because they depend on filter feeding, organic matter in the water column. All of the organisms, including trilobites that would be creeping about on the seabed, have got nothing to feed on, and they die anyway because they have no oxygen. So, and there is a sort of safe zone in the ocean, somewhere between the thermocline and the lack of oxygen area. So at certain seasons of the year, that might have been just inhabitable. So, some life did survive, but the majority was wiped out because of that.
But surely in regards to like that flora and fauna, if so much is wiped out, I mean, I was terrible at biology at school. I gave it up as soon as I could. But the name photosynthesis, sticks in my brain, like carbon dioxide to oxygen. If there is a great reduction in the amount of plants and trees, surely that also means that for those animals that were forced to move, during those thousands, millions of years, the amount that they could breathe in the atmosphere must have been so much lower as well.
Oxygen levels did go down. We're not sure how low they got, but you are absolutely right in terms of the functioning of the Earth. Photosynthesis is hugely important. It's the means, obviously, it's the standard process by which plants convert CO2 into oxygen, but also build their bodies and so on. And we often forget there are photosynthesizing organisms on the surface of the ocean, and they provide the oxygen, a lot of the oxygen for the ocean. But if you perturb all of that, yes, the CO2 levels went up, oxygen levels went down. I think animals can adapt to low levels of oxygen. If you think of, human athletes can limit the amount of oxygen and still function. People can live in Mexico City and in Tibet. They're not comfortable, but it doesn't kill them. So I think the lack of oxygen was there. That was real. And it would have taken maybe 5 or 10 million years for plants to recover sufficiently to build up again to the level of photosynthesis that had been going on before the crisis.
Well, let's get on then to what died. Mike, if we keep on the land first of all, what types of animals, what were the main ones that really suffered? What types of animals died in this mass extinction event?
It was mainly the big ones. They're always at risk. So those pariasaurs and the great one-ton herbivores and the saber-toothed gorgonopsians, but a whole lot of other big and unusual and extraordinary reptiles disappeared on land. There were extinctions of plants and insects. It's debated how much, because extinction can kill species. It can also restrict the relative abundances. So for plants and insects, it may have been as much killing off individuals, reducing biomass, as killing species. But it did reduce the numbers of vertebrates on land hugely, to the extent that in the Triassic, it was a whole new world. You can see it when evolution started again. The survivors were a quite limited number. And some of the survivors founded these new lineages. Others are what have been called dead-clade walking, which means they survived, but they didn't actually flourish. And the time of crisis, there are sort of disaster species that can survive in some way or other in a crisis time. And it's something like the succession of plants on the banks of a major excavation, like a motorway cutting. Certain weeds will come back for a short time, but they're soon swamped out by grass and bushes and so on. And in the oceans, all the reef-building organisms disappeared. Most of the fish groups, except for a few survivors, a lot of brachiopods disappeared. And so there was sort of devastation in terms of numbers of species, but also, I think, in terms of the abundance, the kind of biomass as well.
And then we do get that figure, isn't it? 96% or 97%? I mean, how accurate do we think that is as an estimate for how much life died?
There are two ways people have estimated it. It's been done at a regional scale. So in South China, where people have been able to document this in a lot of detail, there were the two events with about 80% extinction each, which with originations and other activity sums up to about 96% in that region. Is that global? People have estimated, you can't really count it globally because there are so many parts of the world where the documentation isn't very good, so we just can't be sure. But another way of calculating it is sort of back counting. If we, life is divided up into species, and then species sit within genera sit within families, orders, etc., that big classification of life. So it's easier to estimate the extinction of the higher groups like orders and families. And there's a way of linking the two. So there's a kind of relationship between the rate of loss at the higher level and the lower level. It's bigger at the lower level because to wipe out a family, you may have to kill 100 species. And therefore, if a family survives, it may only have 2 species in it, but it survives. So there's a sort of relativistic way of calculating this called rarefaction. And using that, it's possible to calculate from maybe a loss of 40% of families equates to 60 or 70% of genera, which equates to something like 95% of species. So the two observations converge, and that's why, and they come from different ways of thinking, and that's why we come up with the figure of 95 or 96%.
It's almost like sharks, isn't it? Often labeled as the great survivors through all of these hundreds of millions of years. And yet, the great diversification of these different shark groups, most of them do go extinct, but a handful, because they are so diverse, a handful do survive that have come down to us today.
That's right.
And are there some notable survivors that we should mention on land and at sea? I have watched Walking with Dinosaurs, and I remember episode 1 that seems to have, mentioned some Triassic animals that came from an earlier period. So what do we know about those?
I think on land, there were lots of plants and insects survived, and then they diversified and new groups of plants appeared. For example, modern type conifers appeared at the end of the Triassic. So ancestors of monkey puzzles and spruces and firs and so on, they appear. But also amongst the reptiles, 2 key groups, there were the cynodonts, which are proto-mammals, and they include our ancestors. So the first mammals appear near the end of the Triassic from these cynodonts, which survived from the late Permian. And on the other hand, there were some of the early archosaurs, which emerged also at the end of the Permian, and they did survive. And the archosaurs today are represented by birds and crocodiles. But I like the word archosaur. It means ruling reptile. And they did give rise to the dinosaurs, which, of course, are ancestors of birds. So the dinosaurs emerge probably quite early in the Triassic. We don't really know for sure. But they were pretty diverse and dominant by the end of the Triassic. So on land, these were some key groups that emerged and really were important.
And what about this big, ugly group of herbivores that it seems important to mention? I know they talk about the Placerias in Walking with Dinosaurs, but they also Lystrosaurus. Is that what their name was?
The great survivor was Lystrosaurus, which is a dicynodont. These are herbivorous proto-mammals. They did do very well. They were very important in the late Permian, and they bounced back. And Lystrosaurus itself seems to have been one of these kind of disaster species. It somehow or other, probably because it could burrow in and make itself burrows and hide away in the heat of the day, and somehow survived in all parts of the world. In the end, it was short-lived, but it was in its day, it was very important, very dominant animal, and gave way in the end to others. And then towards the end of the Triassic, there were giant ones like Placerias, and there were other relatives, some of which reached a ton in weight, but they eventually died out at the end of the Triassic.
And in the sea, what are the other notable survivors we should mention?
I think in the sea, most major groups survived in one way or another. The brachiopods, the mollusks, the arthropods, the echinoderms, all the various wormy creatures in the oceans, and of course the fishes in general. But they were different forms. So amongst the arthropods, the trilobites had entirely gone, and we get crustaceans instead. So things like lobsters and crabs begin at that time. And whereas the brachiopods did survive, they never recovered. They used to be the dominant seashells, essentially. And on the other hand, mollusks did so much better. The bivalves, gastropods, cephalopods, and the clams and so on, they really bounced back, and they're the dominant, in the form of oysters and scallops and all kinds of, and snails and whelks and such like today. Amongst the fishes, various bony fishes and sharks of a more modern kind emerged. So in fact, people often quite reasonably track a lot of life in the oceans today back to the Triassic. And at the start, you joked, yes, we call the dinosaurs modern. Well, yeah, actually, the modern marine fauna, what we see on the coral reef, what we see being fished up out of the oceans around the northern continents, this is the modern marine fauna, and a lot of it does actually track back to the Triassic. So the end Permian extinction event was highly catastrophic. It was huge. It was the biggest of all time. But it actually triggered an amazing evolutionary response and sort of marks a very major reset of evolution of life.
Ultimately paves the way for the rise of the dinosaurs, doesn't it?
Indeed so. Indeed so.
The Triassic is often pictured as quite an arid, difficult time for life, this time of recovery from this mass extinction event. How long would you say it takes for the Earth to fully recover from the Permian extinction?
This is an extraordinary phenomenon that, of course, yes, you're right, these crises are not quick. And it probably took the Earth minimally maybe 10 or 15 million years. And the evidence for that is that we see constant perturbation of oceans and atmospheres for at least 6 or 7 million years after the crisis, before temperatures and so on stabilized, and then life could begin to evolve in a more normal way. But I think also reefs had disappeared in the oceans, and forests had disappeared on land. So these are big structuring components of biodiversity. And if you delete reefs and delete forests, that's quite a startling phenomenon. And so it took maybe 15 million years for those two to come back. And so that's why I mentioned that time, because the Earth, I guess, physically has to stabilize climates and all the other physical phenomena. Then life takes a while to accommodate itself, because if you perturb life in various ways, things go extinct and it starts again. And you need that stability for ecosystems to build up the kind of complex relationships that describe a forest or a reef. So, yeah, it had long-term effects.
I've got to ask, as we've got you here, very briefly right at the end, Mike, are we due another mass extinction?
We are due another mass extinction, but when is impossible to say. At one point, people thought they were periodic and hence predictable, but I don't think there's a great deal of evidence for that at the moment. If we know that the main cause is massive volcanic eruption, then there surely are ways of detecting that using seismology. We can detect, we're not very good at detecting when a volcano is going to go off. It used to be people thought they were all caused by asteroid impacts, meteorite impacts. And I remember politicians talking about issuing us with hard hats, if they thought an asteroid or meteorite was approaching. But there's probably nothing we can do about it. But the main cause does seem to be volcanic eruption rather than impact. So that's something we've learned.
Mike, this has been such a fascinating chat about this extraordinary event from our distant past. And you have written several books about the Permian extinction and extinctions in general over the years.
Yes, there's been because I've been involved, I've loved talking about it. I have a book I wrote a while ago called When Life Nearly Died, and that describes that particular phenomenon. I've written about extinction events also in general in a book called Simply Extinctions, How Life Adapts, Dies Out and Survives. They're available, and yeah, I'm really keen to transmit this current information to people.
Well, Mike, this has been absolutely fascinating. It just goes to me to say thank you so much for taking the time to come on the podcast today.
A great pleasure. Thank you.
Well, there you go. There was Professor Michael Benton talking through the Permian extinction, the greatest mass extinction event ever to hit planet Earth. And that brings us to the end of our Great Disasters mini-series this September. I hope you enjoyed it. Stay tuned for our next mini-series in a few months' time. What it will be, well, you'll have to wait and see. Thank you for listening to this episode of The Ancients. Please follow the show on Spotify or wherever you get your podcasts. That really helps us, and you'll be doing us a big favour. If you'd be kind enough to leave us a rating as well, we'd really appreciate that. Don't forget, you can also listen to us and all of History Hits podcasts ad-free, and watch hundreds of TV documentaries when you subscribe at historyhit.com/subscribe. That's enough from me. I'll see you in the next episode.